Hello guys, I am Dr. Devendra Mishra, working as Assistant Professor in Chemistry at Bidla Institute of Applied Sciences, right? Also running this tetrahedron chemistry classes channel, and here are the links available to approach me. Hello friends, welcome back to the tetrahedron chemistry classes. So guys, it is my lecture number 12C, and in this lecture I am going to discuss the migratory insertions reactions, okay? And if you are following my organometallic lecture series, then you are already aware about the fact that I have completed the oxidative addition and reductive elimination reactions in a pretty much detail, right? And in this third part, 12C, I am going to cover this migratory insertions reactions. But guys, since this is the festive season and my vacation is also going on, and unfortunately I forgot my mic in my institute. Okay, so there may be some voice issues with these lectures which I will post during this period, right? Say from today up to 16th November, if whatever I will post, they may have some mic issues, not necessary, but they may have. And since this is the Diwali season, festive season, you may also hear some sounds of the firecracker. So kindly adjust all these things. Okay. So today I'm going to discuss this migratory insertion reaction, and I'll call these reactions as MI reactions. Okay. So this is the abbreviation MI which I have given to these reactions, and these are the very important reaction when it comes to the Csir Net and the gate examination, and also for the IIT JAM also, right? And see, if you are doing your MSc and you have this organometallic paper as a specialization, then this lecture series is going to be very important for you. Okay, so what are these migratory insertion reactions? You can see we may have some small molecules, like you may have this carbonyl group, and along with the carbonyl you may have your alkene. Okay, and apart from this alkene you may have your alkyne. These are the small molecules, and you may also have like SO2, sulfur dioxide. These all are the small molecules, and these molecules what can do, they may be inserted into the metal carbon bond, okay, and they may also be inserted in the metal hydrogen bond. So what you will do, you will take this carbonyl, you can insert this carbonyl in between these two bonds. You may insert this carbonyl between this metal and hydrogen bond, and same is true for these alkene, alkyne and the SO2. You may insert this alkene in between these two groups. So basically the migratory insertion reactions are those reactions in which the small molecules may be inserted into the metal and the ligand bond. Ligand may be your carbon and maybe your hydrogen, very common one. You may have the nitrogen also, metal nitrogen bond you may also have, and you may have also the metal oxygen bond. But these last two categories are very rare, so we will not discuss these. These are the rare examples, but we will see the insertion of these small ligands into the MC bond and in the MH bond. Okay, and these when it comes to this migratory insertion reactions, so basically these reactions are of two types. So first of all, you should know what is the difference between the different kinds of the migratory insertion reaction. So first I am giving you the example of the 1,1 migratory insertion reactions. And see guys, you may call these reaction as insertion reactions, you may call these reactions as migratory insertion reactions, right? Any name you can give. So first I am going to discuss this 1,1 migratory insertion reaction. So for this I will take a very simple example, and then you will know how actually these reactions proceeds. Say this is my manganese, okay, and I'm doing for the octahedral complex, okay, and say this is my octahedral complex, and here some alkyl group CH3 is attached, okay, and various carbonyl groups are also theirs. So guys, this is the trick for you. If you see this carbonyl group along with the CH3 group, then always the reaction will be your migratory insertion reaction. Presence of your small unsaturated ligand along with the sigma donor ligand. This CH3 is the sigma donor ligand. So this sigma donor ligand adjacent to this carbonyl group to the cis position. When you find this kind of situation, you may quickly predict that okay, the reaction is going to be the migratory insertion reactions. Okay, and what I can do, I can react with this reaction with say triphenyl phosphine. Since the pH, you know, this is the phenyl group and 3 phenyl groups are attached here, and if you do the reaction with this one, then it is going to be the 1,1 migratory insertion reactions, and in that case your product would be just like that, right? This is say your octahedral complex. So what you can do, carbon double bond oxygen, say this one, and this is your CH3. There is no problem in that, and this pH3 will take the position of this CH3, and you can write PPH3 here, and this is your carbonyl, this is your carbonyl, and this is where yet another carbonyl along with this one. This is the carbonyl group. So this is 1,1 migratory insertion reaction, and why I am calling this reaction as the migratory insertion reaction, you can observe first this CH3 will migrate to the CO ligand, and to which CO ligand it will migrate, I will discuss these things in the detail little later. Okay, so this CH3 first migrating to this position, and at this position this ligand is actually PPH3 is occupying that particular site. So migration of this CH3 and then the insertion of this PPH3 is going on. That's why the reaction name is the migratory insertion reaction. And why I am calling this reaction as 1,1 migratory insertion reaction. See, what happens in the 1,1 migratory insertion reactions, the metal, say this is your metal, so sorry, it should be manganese. Okay, this is manganese, this should also be manganese, the metal and the migrated ligand. So this is the manganese, and this CH3 is the migrated ligand which have migrated from this position to this position. When this metal and the migrated ligand forms the bond with the same atom of the unsaturated group, then it is known as the 1,1 migratory insertion reaction. So in that case, this is your unsaturated ligand small, and with the carbon atom is common, and this carbon atom is forming bond with this migrated ligand as well as with the metal. When this happens, then the reaction is said to be 1,1 migratory insertion reactions. Then I am going to discuss a second very important category, 1,2 migratory insertion reactions. Okay, and for this I'll take a very simplest example. I'm not going to actually make a giant structure like just like this, and in that case what happened, you can see here, say this is my metal, it could be anything, and say this is my ligand, and see generally this ligand is hydrogen, but not necessarily this is always be a hydrogen, it may be your alkyl group also, and you have the alkyl, you have this alkene, right? So again I am giving you the situation, whenever in this kind of the reaction you are finding the alkene group instead of this PPH3 small, then it will always be the 1,2 migratory insertion reaction. So what will happen in that case, say this ligand will migrate, and this metal and this migrated ligand will form the bond with the different atoms of the unsaturated ligand. So basically it is what? It is CH2, it is also CH2. Okay, and when the product will form the metal, and one carbon will form bond with that metal, and this is another CH2 group, and then your ligand. Okay, so this L is the migrated ligand, and this is the metal, and when this happens, actually when metal and the migrated ligand forms with a bond bond with the different atoms of the unsaturated ligands, then it is known as the 1,2 migratory insertion reactions. Okay, so first of all you have to understand these things, rest of the features you can leave, and now I am going to discuss the very important, the salient features of these reactions, and these features however very important for your theory examination when you are going to when you are doing your MSc program. Okay, so these are the some of the features. I am quickly reading this reaction. these features, and then we'll apply these features on the migratory insertion reactions. So first of all, change in the oxidation state. Sorry, I should put my paper in that way. Change in the oxidation state would be 0. Okay, so what is the meaning of that? Whenever the migratory insertion reactions takes place, then the metal, transition metal, will have no change in the oxidation state. For example, in that case, you can observe manganese attached with the CH3, it is having the +1 oxidation state, and when it will form this particular product, then manganese will again have the same +1 oxidation state. So no change in the formal oxidation state of the metal during the migratory insertion reactions. And second point, migratory insertion reaction creates a vacant site which is being occupied by the incoming ligand. This point I will explain when I will do the mechanism of this particular reaction. So what happens in that case? Actually, this methyl will migrate from here to here, and here it will leave a vacant site, and this vacant site would be occupied by this PPH3. Okay, this is the meaning of that, the side of this second point. And the two ligands undergoing migratory insertion reactions must have the cis relationship. What is the meaning of that? You can see here, this CH3 and this CO, they are having the cis relationship because the angle between them is 90 degree. Similarly, this and this is also forming the 90 degree bond angle. This and this is also forming 90 degree. This and this also forming 90 degree. So your CH3 can migrate to this, can migrate to this, can migrate to this, can migrate to this. That means it will have the 4 different options to migrate, but it will never migrate to this CO ligand. This transposition actually is not there to migrate actually. Why? See, when you see the proper mechanism, then actually the formation of the transition state is not favorable to the trans relationship. So this migration will always occur to the cis CO, not to the trans CO. Okay, so this is your third point. And migration reactions, migratory insertion reactions usually favored on the more electron deficient metal, right? This is quite obvious, guys. See, whenever you have given the two complexes and you are having the same metal, in that case, one is having more electron rich and other is actually electron deficient. So the rate of the reaction would be faster for the electron deficient species. Why? Because these electron deficient species can actually accept the electron pair from these ligands, and to accept the electron pair from the ligand, they should have the less electrons, right? So for migratory insertion reactions to occur, the metal should be electron deficient metal. Okay, then the point number 5, presence of the alkyl group is the indication of the 1,1 migration. I have already told you, whenever you are finding the alkyl group along with the carbonyl group, right, or any other unsaturated group, then there is always a chance of your 1,1 migration, 1,1 migration reactions. And these 1,1 migration reactions, they are very common in the metal alkyl bond. Okay, and then you see, more electron rich alkyl group will migrate first. Say you have see, in that case you are having this CH3, and apart from this CH3, say you are having the tertiary butyl group, just like that. Then you will have two alkyl groups, alkyl and tertiary butyl group. Then which one will migrate? Obviously the more nucleophilic, which will have the more electron density, it will migrate first actually. Okay, because they have to donate the electron to the metal. Okay, that's why electron rich ligand, electron rich sigma donor ligand will migrate first. So more electron rich alkyl group will migrate first, and this is the order actually. Tertiary butyl, right, it is having bulky and it is more nucleophilic, having more electron density due to the plus I effect of the 4 alkyl group. This comes from the basics of the organic chemistry, and I hope you are aware about the basic organic chemistry. Then there comes the 3 carbon species isopropyl group. Okay, then the second number comes for this one, then for the ethyl, and then for the methyl, and finally for the this benzyl. Okay, so why? Because this CH2, this negative charge is not really present on this particular carbon, it is resonating over the ring. That's why the negative charge is not very much there on that, but on this particular carbon atom. So it is not that electron rich. Okay, and then the point number 7, migratory insertion reactions are is possible for the ligands of like CH through CO, PME3 and PH3. Obviously the rate would be faster when you have the carbonyl group, but when you have this PME3 and PH3, and rather I should write PPH3, triphenyl phosphine, when you compare these two, so this PME3 is more electron rich. Why? This 3-methyl group actually, due to the plus I effect, will increase the electron density on the phosphorus, right? So it is more electron rich, so it will have the more tendency to undergo the reaction when compared to the PPH3, because it is a better donor, right? So better donor like PME3, which is greater than the PPH3, have greater tendency to displace the alkyl group in the migratory insertion reaction. This may point, actually this particular point may become important when you have you may have the question based on this. Okay, and then if a migratory ligand is the, see, this is something very important. If the migratory ligand is chiral, see, you have seen this particular example, this is the migratory ligand. If this is chiral and it is migrating, then of course when the migratory insertion reaction occurs, it occurs with the retention of the configuration. So the configuration, see, say if it is R and it is migrating and migratory insertion reactions is going on, so it will become R on migration. It will not change its configuration. Okay, so this is called the retention of configuration during the migratory insertion reactions. And this CO insertion, if you want to do the carbonyl insertion reaction, then it usually takes place in the metal alkyl bond. And whenever you have the metal alkyl bond and you are doing this carbonyl insertion, CO insertion reaction, then the mechanism would be 1,1 insertion reaction. Okay, as I have explained here, alkyl and carbonyl, so it is 1,1 insertion reaction, because this is MR bond, right? So when you are having this MR bond, then 1,1 migratory insertion reactions are very common. Okay. And then alkene insertion, if you want to do the alkene insertion reaction, then there should be the presence of the MH bond. So what is the meaning of the MH bond? It should be just like that, MH. Okay, then this hydrogen will migrate. If you do the same reaction with this one, CH2 double bond CH2, okay, so this hydrogen will migrate from here and you will have metal, CH2 and CH3, this kind of compound you will get. So this will you can predict whenever the hydrogen is there, then the rate of this 1,2 insertion reactions would be very fast. However, this migratory insertion reaction can also take place when you have the MR bond, but the rate in that case would be slow. Okay, and then you can see usually the 18 electron complexes favors the migratory insertion reactions. This is another feature. Okay, and bulky ligand and the Lewis acid, if you have the bulky ligand, like I have told you with the help of the tertiary butyl example, right, and along, see, bulky ligand can enhance the rate of the reaction. If you have the Lewis acid, electron pair acceptor, they will also actually enhance the rate of the reaction. However, I am not going to discuss the details of this one. Okay, and when you are doing the 1,2 migration insertion reactions, like in case of this alkene reaction, right, alkene insertion reaction, so there would be the change in the hapticity. Eta 2 will become the eta 1. Okay, and of course migratory insertion reactions, whether you are doing your say 1,2 insertion or 1,1 insertion, they are always the stereoselective reactions. And stereoselective reaction, I have made a lecture on this. What you can do, if you don't know what are the stereoselective reaction, and if you have the little doubt on this, but on the explanation of this stereoselective reaction, then you can type in the YouTube search bar stereoselective reactions by tetrahedron chemistry classes. Then you will find a very beautiful explanation for this one. Okay, so for your information, if you are new here and you are not aware about the stereoselective reaction, I'm telling you, a reaction which is producing more than one stereoisomers, and one stereoisomer actually is predominates, then such reactions are called the stereoselective reaction, and this happens in the migratory insertion reactions. That's why these reactions are your stereoselective reaction. So these are the features you have to keep in mind, and I'll discuss these features again and again. Okay, so this is how you can take the examples of your migratory 1, 2 and 1,1 migratory insertion reaction. So now I am going to discuss some very important reactions, and these reactions are very important for any examination, right? And I'm going to discuss first to say CO insertion, carbonyl insertion. Okay, you may call this reaction as carbonyl insertion, and other name of this is carbonylation. Carbonylation. Okay, and you know this carbonylation or insertion, this CO insertion is basically what? It proceeds through alkyl migration. Alkyl migration. Okay, so you may call this reaction by any name depending on your choice. Actually, you may call it as CO insertion, you may call it as carbonylation, you may call it as alkyl migration reaction. So guys, there are different kinds of the mechanism proposed for this reaction. However, experimentally observed yield supports only one of the mechanism, but for your knowledge, actually I'll discuss all the three mechanisms. So first of all, you can see what will happen in that in this particular reaction. So I am going to discuss the mechanism 1, say. Okay, and say you are having this your old friend, this particular complex which I have for which I have started my lecture itself. Say this is carbonyl, this is another carbonyl, and this is my alkyl group, right? Remember, this must be the sigma donor. Okay, this must be the sigma donor, and this is my another carbonyl. Okay, and these are the carbonyls, right? And say it is in +1 oxidation state. So what will happen in the first instance? It's a reversible reaction, rate constant, that is the K1, right? And what will happen? The migration would occur, and I told you, see, this R can migrate to this position, 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 but it cannot migrate to this particular position because they are having the trans relationship. Whenever your carbonyl group and R having the trans relationship, the migration would not occur to this particular position. So how many choices are there? 1, 2, 3, 4. 4 choices are available for this alkyl group to migrate, actually, right? So what will happen in that case? Say this R is migrating, and for your convenience, I am migrating this R on this particular, because they are having the 90-degree relationship, cis relationship, and then you will have, say, your manganese, right? This carbonyl would be untouched, this would be also untouched, this would be also untouched, and this would be also untouched, and now this has migrated. So you know, carbonyl is what? Carbon triple bond oxygen. So one of the bond would be used to form the bond with this one, right? So you can write carbon double bond oxygen, and this is my migrated group R, and this will leave a vacant site. So there are different ways in the literature. There are different ways available in the literature to show the vacant site. So this actually rectangular shape of box is showing the vacant site. So this is your vacant site, right? And remember, it was 18 electron species. You can count the electrons of all of them, actually, right? It is 18 electron species. I'm not going to discuss the nature of the 18 electron system, how you can count, because I have explained all these things in pretty much detail in my earlier lectures. And when it loses one of the ligand to the neighboring ligand, right, obviously it will become 16 electron system. Okay, and here it is octahedral, no problem, and here 1, 2, 3, 4, 5. However, it is not looking like that, but the structure of this one is trigonal bipyramidal structure. Okay, so 4 options are available, but I have shown only one option for available for this R to migrate from this particular position. You can consider all of them, right? And this is your alkyl migration, and this alkyl migration is very well supported by the what? Your experimental results. So in the next step, what will happen? Say you are having another carbonyl, and to differentiate between the carbonyl groups which are present in the molecule and the carbonyl group which is coming as the ligand, I am labeling it with the C13 isotope. When I label this with the C13 isotope, then my product would be just like that: manganese, carbonyl, this is another carbonyl, this is carbonyl, but it is C13 because I have labeled it, and this C13 will actually occupy this particular vacant site. Okay, and this is where C double bond OR, and this is CO. So basically you are forming acyl bond actually. See, acyl groups are very common in the organic chemistry. I hope you are aware. Okay, and of course the oxidation state would be 1 in that case. So if you apply all the features which you have shown in the earlier slide actually, so you will find all the things as such actually. It is 18 electron system, favorable, presence of the R and CO. It is the condition for the 1-1 migration. So basically this CO insertion is what? It is 1,1 migratory insertion reaction. So this is 1,1 migratory insertion reactions. Okay, so this particular mechanism, which is actually the alkyl migration, it is very well supported by the experimental results, and you will always look for this particular mechanism. Always look for this particular mechanism. I will prove this actually fact with the decarbonylation reaction little later on. So this is the mechanism one, which is the most favorable one. Okay, now say I'm having my next mechanism, which is the mechanism number 2. First I have explained the alkyl migration. Now I am going to discuss direct insertion. Direct insertion of incoming CO into metal alkyl bond. Okay, now I'm going to this particular one. So how this happens? Okay, say you are having your manganese, your carbonyl, your CH3, your CO, and your remaining CO. Okay, right? And say you are attacking this complex with this CO, which is C13 labeled. So in that case, what product you will expect? Mn. So I'm explaining in that way. This is coming and it is directly going in between manganese and the CH3 bond. So this is direct insertion of the incoming ligand into the manganese and the CH3, that is the MR bond. So what product you will have? C double bond O, CH3. Okay, rest are your carbonyl groups. Okay, carbonyl groups, right? So obviously in that case what would happen? This particular which is inserting here, it should be C13 labeled. This carbon should be C13 labeled, but when you do the reaction in lab and isolate your product, then you will never find this particular product. When you are not finding this particular product, that means this reaction, this mechanism is not a good mechanism, and it is not well supported by the experimentally found results. Okay, so because why this happens actually, if you go for the kinetic factors, so activation energy for this reaction is very much high. So this process is not feasible. So you will not go for this particular, you will not look for this particular mechanism when you are discussing 1,1 migratory insertion reactions. And then there comes the mechanism number 3, that is part 3. Here I am calling it as intramolecular carbonyl insertion. Okay, so this particular mechanism, right, it is having actually the average activation energy. This mechanism is possible based on the activation energy, but again the experimental results actually does not support this mechanism also. Okay, so how you can see, so I'm doing this reaction with the same example. Okay, all these things you will bear in your mind, that cis relationship between the carbonyl and the alkyl group and no change in the oxidation state, right? All these features you should know. This is CH3. Okay, now what will happen? I'm going to discuss the intramolecular CO insertion. That means within the molecule, one of the CO group which is cis to this CH3 will actually insert. So this can insert, this can insert, this can insert, this can insert, but this cannot, because this and this having the trans relationship. So for simplicity, I'm going to discuss only one way. Say it is actually inserting here. It is inserting here, and when it is inserting here, then definitely you will have here this particular product, Mn C double bond O CH3, and of course this is your vacant site along with your carbonyls, okay, along with your carbonyls. And finally what you will do, you will actually react with this this complex with your 13C labeled CO, and you will have your product. So what product you will expect? This will insert here actually, and you will have Mn CO13, right, and C double bond O CH3, and rest of the carbonyl groups. So this is intramolecular insertion. See, kinetically it is favorable mechanism, but experimental need does not support fully this mechanism also. So basically three different kinds of the mechanisms are there. First is your alkyl migration, okay, which is the most favorable one, and experiment supports it. And then these are the two mechanisms which this is not possible at all due to the very high activation energy. This is possible, but experiment does not support. So how we can prove actually the alkyl migration is going on? So we will discuss this thing, and you may have the question in your examination gate or your net examination based on this particular complex. For this we will use the decarbonylation reaction, okay. So here I am doing decarbonylation. Earlier I have done the carbonylation, that means insertion of the carbonyl group. Now I'll do the decarbonylation, that means removal of the carbonyl group, okay. Decarbonylation reaction, which is basically the proof of the alkyl migration. So I can take the different example. First I'm taking, say, CO migration pathway. CO migration pathway means intramolecularly this one. I'm going to discuss this one, and I'll not discuss this one. Why? Because it is not actually there. So I'm going to discuss this one. For this actually I'll take this particular example, like Mn CO13 labeled with carbons 13, and these are the carbonyl groups, and this is your COCH3. So this is not in the frame, don't worry, I am dragging the paper in the frame, okay. Now you see what path I am taking. I am taking this particular CO migration pathway. CO migration pathway. That means I will migrate this CO. I am taking this particular pathway. I am starting with this particular product, because I am doing the decarbonylation. So in that case what will happen? This will leave from here to here, and this carbonyl actually will move onto this metal. When it will move to this particular metal, this will knocked out, and this carbonyl will take the place of this particular 13C labeled CO group. So here I am writing minus CO13. It is leaving from here. Then you will have your original complex, Mn and CH3. This is CO. All 5 COs are there. So this is the starting product actually, this particular one. So this is decarbonylation reaction which I have done here, okay. And see, because you remove this particular 13 CO from here, so basically what is the probability? See this cannot migrate to this particular position, because they are having the trans relationship. So option 1, option 2, option 3 and option 4, This can eliminate, this can eliminate, this can eliminate, this can eliminate, but this cannot eliminate because they are having the trans relationship. Okay, so 4 options are available. I have, that means total 25 into 4 makes 100. That means when you take the 100%, then the 25% probability of eliminating each of the CO group. So when you are removing this 13 CO, so what is the probability? It is only 25% probability to remove that this particular 13 CO labeled. So the product will, you will have the product which will have unlabeled carbonyl group. Unlabeled carbonyl group. Okay, so this is 25% probability. And then guys, I'm going to discuss, say, next. I'll take the next page for this one. You keep in mind this particular fact. And say, now I am doing the decarbonylation reaction. Say this is my manganese. And again I am starting with this same starting material. With this starting material I am doing the reaction. Okay, so these are the carbonyls, and this is your Ethyl group, and this is your carbonyl. You have removed this one. Okay, so there is no need to remove this one. Now how many choices are available to remove? You can remove this cis relationship, you can remove this cis relationship, you can remove this cis relationship. You cannot remove this. Why? Because they are having the trans relationship. So if you follow the 3 different paths, then you will have your product always just like that. Mn CO labeled 13. Okay, and your CO is here, and this is your CH3, and this is CO, this is CO, and this is CO. So this is the product. See, earlier what product you were getting? You were getting the product which is not having the labeled carbonyl group, but in that case you are having the labeled carbonyl group. So I have put this labeled carbonyl group here in that case. So it will remain as such. So in that case, see what different options are available. See, I can move this from here to here. Then this can remove from here, minus CO I can write. First option, because they are cis. And I can see, for better understanding, better explanation, I can actually move this from here to here. This can remove. This is option number 1. I can move this carbonyl to this particular position. This can remove. Option number 2. I can remove this. I can move this carbonyl to this one, and this can remove. So this is third option. So what is the percentage? Total 75% probability would be there. 25 for this first route, 25 for this second route, and 25% for this third route. So total 75%. But experimentally this is not found actually. Experimentally this is not found that you are getting the 75% of this labeled carbonyl group, the complex with the labeled carbonyl group. 75% it is assuming in that case if you follow the CO migration pathway, but experimentally it is not found. So when it is not experimentally found, that means this decarbonylation reaction, right, and that means the CO migration pathway is not a very feasible pathway. So I have already told you this is feasible kinetically, but practically it is not. Experimentally it is not found. But what experimentally we found? We found experimentally the first one, the alkyl migration one. So now I am going to discuss the second pathway. Now we can see the methyl migration pathway, how the reaction takes place, and what is the percentage of the different kinds of the products when we actually follow the methyl migration pathway. And this would be proved by the experiments also. So this is the actual mechanism which takes place in the carbonylation reaction, okay, which is what your L-methyl migration reaction 1,1 migratory insertion reactions. Okay, so again I'm taking the same example. Say in the center I am writing by manganese, and this is my 13C labeled carbonyl group, and this was my product. Because I'm doing decarbonylation, so I should start with this product, okay, as I did in the earlier cases. And say this is your carbonyl, this is another carbonyl, this is another carbonyl, and this is another carbonyl. Okay, so which pathway I am following in the present case? I am following the methyl migration pathway. So first of all I am doing this reaction, and in this reaction what I'll do, this methyl which is here, it will migrate to this metal, and this 13C labeled carbonyl will be eliminated from here. So I can write minus CO13, and I have my product in this way. This is CH3 which is here, and this is my carbonyl, and all other carbonyls are there. Okay, got it? So this is my one of the product if I follow the methyl migration. And then again I follow the methyl migration in different way. Say path 2 I am taking, and in that case what I am doing, I am migrating this methyl to this manganese and eliminating this carbonyl from here, because they are also cis to each other. Remember the basic fundamentals. We should always do the reaction keeping in mind that the two reactions which are taking part in the migratory insertion reaction must be cis to each other. So this will knocked out from here, and you will have your product. Manganese in the center, carbonyl with labeled carbon because it is here, and then this is carbonyl, and this methyl has migrated here. It will take the position of this carbonyl. This is one carbonyl, this is one carbonyl, and this is another carbonyl. So this is my second product. Okay, now what I left actually, see, I have migrated this methyl from here to here, this here to here. I cannot migrate this methyl from here to here because these are having the trans relationship. So now what are the two options left for me? I can migrate this methyl here and will eject this one. So I am doing this one. Say this methyl is migrating here and this is coming out. Okay, so what product you will get? Manganese in the center, carbonyl, and carbonyl with 13C labeled. Okay, and this is another carbonyl, and this has migrated to this position. This is ejected out, so this would be here. Okay, and these are the two COs. This is my another product, and then I'm having only one option, that is last option. And in this particular option what I'll do, I'll migrate my methyl group to this position, and this will knocked out. Okay, so what product you will have? Manganese, CH3 over there because it is migrated here, and this is 13C labeled carbonyl. This is carbonyl, this is carbonyl, this is carbonyl. So I am getting my product in this way. So what is the probability of having this one? See, all these three having 13C labeled carbonyl, but this is not, and total 4 options are there. So that means 25% we will find this. And see, second option, you can see this methyl group and 13C labeled carbonyl are trans to each other. So this is one way of reacting. This is 25%. Okay, and this product and this product, basically they are same. Why they are same? Because these two are trans, these two are trans, rest all things are same. So these two are identical one. So 25% of this, 25% of this. If I am calling it as A and calling it as B, it is C, it is D, right? So here C and D, they are identical, and they are making 25 plus 25 equals to 50%, and this is making 25%, this is also making 25%. So what is happening in the product which we will see? That's why the reaction is the stereoselective reaction. Stereoselective reaction. Okay. Why? Because we are getting the different stereoisomers, and one kind of isomer is dominating, that is this one, 50% of this one. Okay, so this is the stereoselectivity of the reaction, and in this see 25% this one and 50% this one and this one. And actually when we do the reaction and we isolate the product, we find this kind of product distribution when you do the reaction. Okay, so this proves that this methyl migration pathway is actual pathway which is taking place when we do the carbonylation reaction. So these problems are generally known as the product distribution problems, and these problems, see in the Missler and Tar, this is the book, very famous, Missler and Tar. You can find the problem based on the product distribution in that particular book in the question form. And to solve those problems, what you will do, you will apply the concept which actually I have explained here. Okay, this is all about your decarbonylation reaction. Now see one more important thing which is very, very important, and some of you may have the confusion about that kind of the reaction. See, earlier I have written here, you can see retention of configuration. If a migratory ligand is chiral, this reaction proceeds usually with the retention of configuration, and important thing is that at that carbon center. So for this I have told you, see this time it is not chiral, this CH3 is not chiral, but if it is chiral and it is migrating, then it will not change its configuration. This is the feature of the migratory insertion reaction. But basically when you do the stereochemistry of carbonylation, you will find that in this case the inversion of configuration takes place. Inversion means inversion of entire molecule, not only, or not I'm not talking about this CH3 group. So how this inversion can be proved? Again, this inversion of configuration can be proved only by choosing this methyl migration pathway, because when you do the carbonyl insertion, CO insertion pathway, then in that case generally retention of configuration takes place. So how actually we can prove that this methyl migration pathway or alkyl migration pathway gives the inversion of configuration? We'll see this particular problem here. Okay, so for this what I'll do, say I can call it as stereochemistry of decarbonylation. Okay, now I'm going to explain this particular one. Say I am having this particular complex, this is eta 5CP, cyclopentadienyl anion. It is linked with the iron here, and this is your acyl group. Okay, and this is my carbonyl which is 13C labeled, and this is PPH3, triphenyl phosphine. So this ligand, this ligand, this ligand, and this ligand, all these ligands are actually different. Okay, so that means it's a chiral molecule. It's a chiral molecule, and it is looking like actually tetrahedral structure, but it is not exactly tetrahedral. It is a pseudo tetrahedral structure. So I can call it as pseudo tetrahedral. Not exactly, the bond angles are not same as we found in tetrahedral cases, but the structure is somewhat like your tetrahedral. So I am calling it as pseudo tetrahedral, and I am doing the photolysis of this one. I am shining light on this particular one. So what will have, what is happening in that case here, right? So alkyl migration would occur, right? And when alkyl migration would occur, what can happen in that case? See, I am removing this, I am migrating this methyl here, and I am ejecting out this carbonyl or eliminating this 13C labeled carbonyl from here. So what product I can expect? I can expect Fe. Cp eta 5, okay, and my carbonyl should remain here, my Et would come here, and my triphenyl phosphine would be here. I can expect this particular product. Of course, removal of 13C labeled carbonyl would occur. But when I check when I analyze the structure of the product with the stereochemistry, then I found this particular one, Fe. This is Cp eta 5, okay. This is carbonyl here. This is PPH3, and this is Et. So actually I am getting this particular product, not this particular one. You can see here, in that case, see, I should have this kind of the product due to this migration, but the configuration is inverted now, because this ethyl actually is taking this particular place, and these two are carbonyl and this, they are exchanging positions, okay. So this is inverted product, which I am getting, which generally we get in the reaction, will not get this particular one, okay. So this is your inversion of configuration during the decarbonylation reaction. How we can prove this decarbonylation reaction happens when we follow the methyl migration pathway. So to explain this methyl migration pathway, what we can do, say I'm showing you both the pathways. So first of all, in this particular reaction, I am doing, okay, what I'll do, I'll make a separate structure for this one, otherwise you would have the confusion for this one. Say Fe, Cp eta 5, this is my ethylene, this is my carbonyl, and this is PPH3, okay. And what you will do in that case, right, this is the product. First I am doing CO insertion plus CO, so carbonyl insertion I am doing. So how the carbonyl insertion would occur in that case, this carbonyl would insert between metal and carbon bond, and then you will have your structure Fe eta 5 Cp, and this is insertion which has happened here, okay. And of course, in that case, when this insertion happens, right, then you will have this PH3. So what I can do here, I'm not showing this one, I'm inserting this one, sorry, okay, I'm inserting this one, please correct this one. So this will create a vacant site here. This is the vacant site. Now what I'll do, this is 13C, and this will occupy this particular position, this vacant site, okay. And then your product would be just like that, C double bond O Et, this is 13C labeled carbonyl along with PPH3, and this is Cp eta 5. So this product I'm having, this particular product, okay, you can see here. If I am doing this carbonyl insertion, okay, now I'll follow the ethyl migration pathway. So ethyl migration pathway I'm doing. So in that case, what will happen, this ethyl will migrate to this carbonyl, and you will have Fe cyclopentadiene anion, that is Cp, this is PPH3, okay, and this has migrated from here to here, Et, and this is the vacant site. Because it has migrated, so this has created a vacant site here. While in the CO insertion, this has migrated, so vacant site is created here. Now if you treat this with 13C labeled carbonyl, so this will occupy that particular position, and you will have eta 5CP CO13C labeled C double bond OET and PPH3. Okay guys, so this actually product. So in that case you can see the inversion of configuration had occurred in that case. So this is inverted product, and this is the product with retention. So when CO insertion takes place, the retention occurs, and when methyl migration pathway or ethyl migration pathway or alkyl migration pathway occurs, then your inverted product will get. And experimentally we found this one. So these are the two proofs actually. Whenever you have this option, your say sigma donor ligand with along with carbonyl, which is the unsaturated ligand, then option is what? Option is what? 1,1 migratory insertion reactions, and the pathway is this particular one. It's a alkyl migration pathway, because in this alkyl migration pathway we'll find the experimental results actually. Okay, so this is how you can understand the thing. So this is all about your 1,1 migratory insertion reactions. Now we will see the next reaction, and now my reactions are 1,2 migratory insertion reactions. We'll see the various examples of this reaction, and then we'll solve the problem of the CSIR NET questions. So this is actually this 1,2 migration, as I have already told you, this is olefin insertion, right? This is olefin, you know, doubly bonded compound insertion in which bond? Principally in image bond. What will happen? These doubly bonded compound will insert between the metal and the hydrogen bond most commonly, and this is very famous, and it happens readily. But in some cases this insertion can also takes place in MR bond. However, in some of the textbook it is written that olefin insertion is for your olefin insertion is the insertion of alkene between MH bond, but not in the MR bond. But it is not like that. I have already see, if you see here, CO insertion in the MR bond and alkene insertion in the MH bond, but not always in the MH bond. It may also take place in the MR bond, but most feasible in the MH bond, right? But it can also occur in the MR bond. Okay, so when this will happen, so you will get a product, and this reaction is having immense importance or immense applications in the synthetic chemistry. See, like you can do the catalytic hydrogenation of alkenes, right? And then you can do the hydroformylation reaction. Then you can do the Ziegler-Natta catalysis, the polymerization of the alkenes. So this reaction is very important when you do the polymerization of the reaction. Okay, and whatever, see this H, if H is here, it will migrate. Okay, it will migrate to the beta carbon. If R is there, then it will migrate to the beta carbon, and what it will result? It will result in the metal alkyl complex. When this insertion would occur, then you will have metal alkyl complexes. This is important, right? And very important reaction. So how this reaction would occur, you can understand in that way. Say I am having my metal hydrogen bond, and I'm inserting this doubly bonded compound, and I'm doing 1,2 insertion. So metal would be here, and this is CH2, this is CH2, and this is the hydrogen. So basically what? This alkene, now this is inserted between these bonds, and this is actually what? M, CH2, CH3, metal alkyl complex. Okay, and in that case you can see here the hepaticity is 2, and here it is changing from, and it has changed from 2 to 1. This is the feature actually which I have already explained to you. This is very important reaction. And why it is 1,2 migratory insertion reaction? Because the metal and the migrated hydrogen, they are forming bond with the different atoms of the unsaturated ligand. Okay, so this is very common, right? But this reaction, when you insert this alkene into MH bond, it is very common. And when you insert this alkene, say what you can do, you can do reaction in that way also. So you can find M CH2 CH2R. These reactions also occur, but they are very rare. Okay, but we cannot actually regard, we cannot say that these reactions will not occur actually. So the important thing is what? Important thing is the mechanism of the reaction, how the mechanism goes on. So I'm doing the mechanism. And one more important thing, not necessarily you will always have this alkene, you may have the alkyne also. Okay, so how the reaction goes in that case, you can see, say this is my MR bond. So it will not make any difference if I take the MH bond or the MR bond. Okay, and say this is having my tetramethyl substituted alkene, ethene actually. Okay, 1 2 3, this is butene actually, right? 1 2 3 4, 2 2 dimethyl butene 2. And if you do the reaction with this one, so what will happen? This compound, this will, see, metal is what? This is electron deficient. I already told you in the migratory insertion reaction it should be deficient in electron, so it will accept the electron from here, and this is the connected R. Right, this is how the reaction goes. But if you make the transition state for this one, so in the transition state, this carbon and single bond carbon, right, and then this will form bond with the metal. So since this is the symmetrical alkene, so you can place your metal in the left hand side or in the right hand side, it will not make any difference. And the bond is start breaking between these M and R bond, and the bond will start forming between the carbon and the M bond, and similarly bond will start forming with this carbon and the alkyl group. Okay, and of course the double bond was present here, so it is again diminishing, right? And these are the two alkyl groups which are attached here. So this is transition state. So in that case, you can see, you can very beautifully observe the metal at which the carbon is connected is known as the alpha carbon, and next is the beta carbon. Okay, so this is important to understand the mechanism of the reaction. When you do when you draw this particular mechanism, then you should know the carbon which is connected to the metal is alpha carbon, and next carbon is the beta carbon. Okay, and this beta carbon actually shares the electron with this R, so it will develop a partial positive charge over there, and you know it is having the partial negative charge. Okay, because it is getting the electron. So this is your transition state. This is transition state, and it's a metallocyclobutane. Metallocyclobutane, right? And it will convert into the product. Reversibly, it will convert into the product. So this R will migrate to the beta carbon. Okay, and what product you will have? This R has migrated to the beta carbon, and 2-methyl were already there. Metal would there with the alpha carbon, and this is 2, right? So this is alpha, this is beta, and see, this is addition. And what you are observing in that case here, the important feature which you are observing here, the metal as well as this particular group R, they are on the same side of the carbon skeleton. So it's a cis product. It's a cis product when you consider the chemistry of M and R. So it is actually the syn addition. This addition is what? Syn addition. Syn addition. So this is something very important. So what you are observing here in the cyclic, this is cyclic transition state. Here positive charge is developing on the beta carbon, and this R group is migrating on the alpha carbon as carbene ion. Okay, if hydrogen was there, if I put hydrogen here, then it would migrate as the hydride ion. This is something very important. Okay, however, the migration of H is very facile when compared to the R. That's why I told you this reaction is very facile when you take the hydrogen, but the rate would be slow when you take the R instead of the H. So it's a cis addition, okay, and this is something very important. And see, one may ask this particular question: why this hydrogen migrated very easily and why not this R? Why the rate? Why the difference in the rate? So the simplest answer is that if you are having the H negative, the hydride ion, so it will have the S orbital, right? And this s orbital of hydrogen with this carbon effect very overlap very effectively. So what you can do, when you take the hydrogen instead of the R, then the overlapping between the beta carbon orbitals and this hydrogen is very strong overlapping, very good overlapping. So this reaction is very facile. But if you take the CH3 negative, right, this is anion, carbene ion, so it will have the sp3 hybrid orbital. So this sp3 hybrid orbital of this R and carbon's orbital, the overlap is not very good, and it is understandable if you know the basics of the organic chemistry, right? That's why it is happening here. This is something very important which you should always keep in mind. And and one more thing which you should know: if you are doing the reaction with MR bond, then the strength of this particular bond also decides whether the rate would be the slow or not. So the ease of insertion actually depends upon the strength of this particular bond, right? If it is weak, then the insertion would be easy, I think, right? And when it is strong, then the insertion would not be very easy, right? This is my way of understanding, right? And if you want to know the ease of olefination, that means olefin insertion, then you can take olefin insertion is very high when you take the hydrogen. As I have explained, the sp orbital will overlap very effectively because it is non-directional in nature, okay? It is very high, and followed by this particular one, say CH2. So I am putting N here, this is CH3, and remember N would be either equal to or greater than 2, and then you can go for, it would be something like that, greater than or equal to, with propyl, CH2, CH2, CH3, and then for the methyl, and then for the ethyl. So this order actually you have to remember. See, lots of my subscriber actually generally they comment in my videos and they ask how many exceptions and why we are actually facing so many of exceptions in the chemistry, and all these things we have to mug out. Yes, you have to learn certain things, because without learning those concepts, without learning those exceptions, you will not be able to solve the problems in your Csir Net in the GATE examination, okay? And one more important question which may comes in your mind, the order follows in that way. So here you can see hydrogen is the exception due to this s orbital, but all these are carbene ions and they are having different carbon lengths, and the order shows in that manner. When number of carbons are higher, then rate would be high, that means the reaction is facile, and it follows this order, but it changes here. So why this ethyl actually is very reluctant in this particular 1,2 migratory insertion reaction? And the answer is the agostic interaction. The hydrogen of this if I take these two hydrogens and CH3 carbene ion, right? So this hydrogen actually it will take the part in the agostic interaction with the metal, right, and as well as with the carbon. So it will form a 3-centered 2-electron bond. See, you know the agostic interaction. Basically, agostic interaction describes a particular structure in which your hydrogen atom is bonded to a carbon and a metal atom in a 3-centered 2-electron bond. So it is actually forming, the electrons are engaged everywhere, so the reaction is not very facile. But if you take the methyl, it will not take part in the agostic interaction. Why? See, you can see here, this is 1, and the carbon, say this is 2, this is 1, and this carbon is 2, right? This is 3, this is 4. So the 4-membered ring will form. But if you have methyl group only, then you will have the 3-membered ring, and this 3-membered ring is not very stable. So this methyl will not take part in the agostic interaction, which actually allows him to do the 1,2 migratory insertion reactions. Okay, and then the last thing, and after that I will solve the problems of CSIR net. Okay, so I'm using the same paper actually. These 1,2 insertions, 1,2 migratory insertion reactions, basically they are of two types. Okay, say here intramolecular I am writing, and this one is intramolecular, two kind of the reaction. So if I take this my 1,2 migratory insertion reactions intermolecularly, intermolecularly, then I can take my ligands, then metal and alkyl bond plus this double bond here, and you know this alkene will get inserted in between M and R bond, and you will have Ln M CH2 CH2R. So this is intramolecular. Now I'm going to explain intramolecular. Ln M R, and your alkene is present in the complex itself. So what will happen? This alkene will migrate or will insert in this MR bond, like I did here actually, and your product would be just like that, Ln M R. So these two kinds of the mechanisms, these two kind of the migratory 1,2 migratory insertion reactions actually are there. And if you want to know the applications of these reactions, then Ziegler-Natta polymerization you can take the OXO process, you can take the Wilkinson polymerization, all these things. And when I'll actually teach the catalysis, then I'll explain all these things. In this particular lecture I'm not going to cover those things actually. And before solving the CSIR net problems, one thing I want to tell you, if you have sulfur dioxide, it's a very special kind of the molecule. It can do 1,1 migratory insertion reactions, and it can also do 1,2 migratory insertion reaction. If you want to know how the reactions are happening, then you can check the book A.K. Das. Okay, and I didn't remember the volume, the 7 volumes, and I think in the volume 6 you can find this particular problem. So SO2 can give you these two kind of the reaction. If you don't find the proper literature about this one, then you can comment in the comment section. I'll make a separate video on this, a very short 5 to 10 minutes video on this also. Okay, now finally I'm going to solve some of the CSIR net problems. So my question number 1, which has been asked in the June 2013 CSIR net examination, and question in that case, you can see the question is quite simple. You have given a reaction, and in this particular reaction you have to find what kind of the reaction is this. So immediate answer which you can predict in that case, you can see the alkyl group, methyl group is there, and your carbonyl is also there. So it is actually the migratory methyl migration would occur, and it is the migratory insertion reaction. Okay, and oxidative addition, I have already told you there is no condition for oxidative addition. So if you don't know about the oxidative addition and all these things, you can go through my lectures also. But for this problem to solve, you should focus on this sigma donor ligand, which is methyl. And when this sigma donor is present with the along with the carbonyl in the complex, then straight away you can mark this as the migratory insertions reaction. And then my next problem, which has been asked in the June 2015 and as well as in the 18 examination, right, in the CSIR net. So it's a very important reaction. What they are asking in this particular question, for the reaction of this iron complex with PME3 gives the intermediate. So you have to tell what kind of the intermediate it will form. So see guys, when you have these kinds of the problems, don't actually look for the answers, what answers are given. First you solve problem by your own. So how I can solve? See, this complex I have given, so I can write Fe, and in that case Cp is here. Okay, Cp is here, so I can write Cp. my methyl, this methyl is here, I can write my methyl here, and two carbonyls are there, so I can write one carbonyl here and one carbonyl here. So it is having -1, it is also having the -1, so iron is in +2 oxidation state. Okay, and in that case this methyl can migrate to this carbonyl, this methyl can migrate to this carbonyl. Two options are there. Okay, so basically it is what methyl migration would occur. There is no alkene, so it would not be actually 1,2 methyl migratory insertion reaction. It is 1,1 migratory insertion reaction. So what will happen actually, this methyl will migrate to this carbonyl and you will have Fe2 positive. Okay, and this is your Cp and this is your CCH3 C double bond O, sorry, C double bond O, and this is your CO, and this is the vacant site. This is the vacant site. Now check the options actually, right? So you can see here, in that case hepaticity of this is given as eta 5 and hepaticity is also eta 5 here. So I have already told you or see, I haven't actually mentioned this particular point, what is happening with the hepaticity during this migratory insertion reaction. So I am telling you, when the migratory insertion reactions takes place, there is no change in the hepaticity. When there is no change in the hepaticity, then option 3 cannot be your answer, because hepaticity is 3 here and it was 5 here. Similarly it cannot be your answer. So you have to find in between these two. So what you are finding here, COCH3, and you are finding the COCH3 here, you are finding the carbonyl here, and you are finding the eta 5 here. So this option B is the correct answer. While this cannot be your correct answer, because CH3 separate it is showing, and separately CO3 is not present, CH3 is not present here actually. Okay, so this is how you can solve, and this problem is very particularly important problem. And then guys, you can see here this problem, the reaction of eta 5 of this one with CH3I gives A. Okay, so for this again I have to draw the mechanism. So I am having this complex, say Fe, this is eta 5 Cp and my 2 of this one. Okay, and one negative charge is over there. So if you react with this CH3I, so this is alkyl halide. Alkyl halide undergoes the nucleophilic substitution. So in that case, this complex will act as the nucleophile, right? And it will attack on this CH3, and this iodine, this I negative will be a leaving group here. So basically it's a SN2 reaction. So if you don't know about, if you don't know what are the SN2 reaction, you can Google, you can search in the YouTube SN2 reactions by the tetrahedron chemistry classes, then you will find the results. So I negative would remove from here, and this this CH3 will get bonded to this particular iron. So what complex you are having? Fe, Me, that is CH3, this is Cp, okay, and this is CO, this is another CO. So this is the product A, this is the product A, and it is showing NMR spectrum of A shows the two singlets. So 3:5. See this CH3, it will give the one singlet and the intensity would be 3 because 3 protons are there. And this is Cp. Cp, you know, this one, hydrogen, 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 right? In that case, and hydrogen. It is attached here. 5 hydrogens are there. So it will have here intensity of 5. So you will get the NMR signal which will have the intensity of 3:5. Two signals, one signal for Cp, one signal for this one. So this is the way, actually this is very simple problem. This is not a very complex problem. Okay, and then what it says, what the question says, A on reaction with PPH3. Okay, this particular compound, when you react with this PPH3, so this is the migratory insertion reactions. When you react this with this one, so this is migratory insertion and this is 1,1 migratory insertion reaction, because there is no alkene. If an alkene was there, then you will do the 1,2 migratory insertion reaction. So now what product you will get? Fe, Cp, PPH3, C double bond O, sorry it is not in the frame, this is CH3, this is CO. What will happen in that case? This methyl will migrate to this carbonyl and vacant site would be created, and this vacant site would be taken up by this PPH3. Now you are having this Cp, okay, that means 5 protons are there, so intensity would be 5, one signal for this one, and then you are having this CH3, one signal for this one, intensity would be 3, and then the PPH3, you know, phosphorus bonded with this, okay, and how many hydrogens? 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 and 5, okay, so total 15 hydrogens are there. Yet another signal which will have the intensity of the 15, so you will get 3 signals for the product B. Say if this is B, you will get the 3 signals and it will have the intensity of the 3 for this methyl, intensity of 5 this Cp, and intensity of 15 for this one, right? And this is the question actually. You can see 3 5:5. So what are the A and B? So you have given lots of option. You can mark this as well as this. So these are the problems which are very common in your CSIR net examinations, and you may you may solve your problems from any book. Like you may go for coordination chemistry by Ajay Kumar, and you may go for coordination chemistry by A.K. Das, and you may go for so not coordination chemistry, the organometallic chemistry in both the cases, Ajay Kumar as well as in the A.K. Das, and you can also use the B.D. Gupta. In the exercise part, the problems are solved in the book or itself. So you can find the different kinds of the reaction. So far I have explained you these reactions, right? Oxidative addition, reductive elimination, and migratory insertion reaction. In the next classes I will take the reductive elimination and some more reactions, and after that I will solve the combined problems on the organometallic compounds, because in the CSIR net examination you will have the amalgam of all these problems. That means they will give you the long chain of the reaction, and one will follow the reductive elimination, other will follow the oxidative addition, then migratory insertion, then ligand substitution, then reductive elimination. So you have to identify all these things. So this lecture is quite lengthy, but this is quite useful for the CSIR net GATE and for the MSc students, as well as for the various PhD entrance examinations. This lecture is very important. So that's it for today. In the next class I'll meet you with the reductive elimination and other kinds of the reactions. Okay guys, thank you very much.